Finding a missing angle in a right triangle. It's one of those classic geometry problems that can make you feel like you've hit a wall. But what if I told you there are really only two simple ways you'll ever need to solve it? Well, today we're going to master both of them. You know that feeling, right? You're just staring at this triangle. You know one angle is 90 degrees, but that little question mark in the corner, it's just kind of staring back at you. It is such a common place to get stuck. Well, let's totally clear up that confusion for good. There are two incredibly powerful methods to find any missing angle in a right triangle. And by the end of this, you're going to know exactly which one to grab, every single time. Let's dive into the first one. So, our first tool in the toolkit should feel pretty familiar. It's a basic, fundamental rule of all things geometry, the triangle sum theorem. You know, the best part about this theorem is just how simple it is. I mean, it doesn't matter if the triangle is huge, tiny, stretched out, whatever, the three angles on the inside will always add up to 180 degrees. No exceptions. So just burn this number into your brain, 180 degrees. It is the magic number. Everything we do in this first method comes right back to it. Okay, let's put this into practice right away. Let's say you've got a right triangle, so you know one angle is 90 degrees, and they tell you another one is 45. Step 1, add what you know. 90 plus 45, that's 135. Then you just take that total and subtract it from our magic number, 180. And what's left? 45 degrees. And just like that, you found the missing angle. Easy, right? Let's run that back one more time, just to make sure it really sticks. Okay, new triangle. We've got our 90-degree angle and a little 20-degree angle. First, add them up. 90 plus 20 is 110. Then, subtract 110 from 180, and our missing angle is 70 degrees. See? It's a super quick, clean, and really effective method. But, and there's always a but, isn't there? Here's the catch. The triangle sum theorem is your best friend only when you already know two of the angles. So what happens when the problem looks a little different? What if instead of two angles, you only know two of the triangle's side lengths? All of a sudden, our first method is, well, it's useless. We can't add up angles we don't know. This is where we have to reach for a totally different kind of tool, one that can build a bridge between the side lengths and the angles. And that new tool is called inverse trigonometry. Now listen, don't let the name scare you off. It sounds complicated, but I promise it's not. This is basically the hero of our story when we're dealing with side lengths instead of angles. I mean, that's literally what inverse trig functions are for. Their entire reason for existing is to solve for a missing angle. They were designed specifically for the exact kind of problem we're looking at right now. Think about it like this. You remember regular trig functions, right? Sine, cosine, tangent, SOHCAHTOA. You give them an angle, and they spit out a ratio of side lengths. Well, inverse trig functions do the exact opposite. You give them the ratio of the sides, and they give you back the angle. They literally undo the regular function. On your calculator, this is usually the second or shift key. All right, theory is one thing, but seeing it in action is everything. So let's walk through a bunch of examples to see exactly how this works. This is where it's all going to click. Okay, problem number 1. We need to find angle z. And the problem tells us that the cosine of z is equal to this decimal, 0.1219. So we've got the ratio. Now we just need the angle. So how do we get z by itself? We have to undo that cosine. And to do that, we use the inverse cosine on the other side. So z is going to be equal to the inverse cosine of 0.1219. That's it. The hard part's over. Now you just let your calculator do the work. You just type that in, hit enter, and boom, the answer pops right out, 83.0 degrees. And just like that, you've used a side ratio to find an angle. Pretty cool, right? Let's keep this momentum going. Next up, find angle y. This time, we're told that the tangent of y is the fraction 2 over 3. The setup is exactly the same, we're just using a different function. So, to get y by itself, we take the inverse tangent of 2/3, plug that into the calculator, and out comes 33.7 degrees. See? The pattern holds up perfectly. It's the same move every time. Okay, here's our third one. We need to find angle A, and we know that the sine of A is 0.3765. I bet you can already see exactly what the next step is. And this just shows you how consistent this all is. To find A, you take the inverse sine of 0.3765, punch it in, and there's your answer. 22.1 degrees.
All right, one last practice problem just to really lock this in and make it second nature. We need to find angle B, and we're given that the cosine of B is the fraction 24/65. You know exactly what to do.
And that's the point, right? It doesn't matter if it's sine, cosine, or tangent, or if it's a decimal or a fraction. The method is always the same. To find B, we take the inverse cosine of 24/65, which gives us our final answer for this round, 68.3 degrees. Okay, let's take a breath. We've looked at two totally different methods. Now, let's put them together into one simple toolkit so you know exactly when to reach for each one. This right here, this is basically your cheat sheet. It's the whole thing in a nutshell. When you look at a geometry problem, you just have to ask yourself one question. What information did they give me? If the answer is two angles, you're using the triangle sum theorem. If the answer is two side lengths, you're using inverse trigonometry. It really is that simple. And there you have it. You now have two rock-solid, reliable ways to solve for any missing angle in a right triangle. You're ready to tackle those problems that might have seemed impossible before. So the only question left is, with this new skill in your back pocket, what are you going to solve next?